Okay. So welcome to Math 383 Complex Analysis. Today we're going to do essentially no complex analysis. What I noticed is a large number of people have never seen a rigorous proof of the fundamental theorem of calculus. And so what we're going to do today is we're going to prove the fundamental theorem of calculus and use this as a way to motivate a lot of the results from analysis that we're using in complex analysis. So as we go through and see them, we're going to see, oh yeah, that's what we were using when we were proving the Riemann mapping theorem. Normally when I prove the fundamental theorem of calculus, I'm proving this to students who have not taken real analysis. So I always impose additional restrictions. I assume that my function is not only continuous, but it's also differentiable, and that allows me to bound certain things very easily. What we will do today is we will not assume differentiability, and we will have a little bit more of an involved argument, and this will allow us to talk about uniform continuity, compactness, and stuff like that. All right, I'm going to try to do things on the iPad rather than the screens to just see how well that works, because it's a real pain setting up the external board. All right, so again, we're going to review analysis, especially compact sets and uniform continuity. The goal is to get to a proof of the fundamental theorem of calculus in 50 minutes. All right, so again, as I remarked, if you add additional assumptions, it frequently makes the proof easier. Not always, because sometimes you start trying to think, oh, now that I have this at my disposal, what can I use with it? And sometimes you can get confused. But for the most part, not surprisingly, the more you have at your disposal, the easier an argument should be because you have more powerful tools. All right, so just to quickly review some results from from analysis that you should have seen is the least upper bound property. So at some point in your life, if you're going to be a mathematician, you should see the construction of the real numbers. If you don't teach analysis, once is enough. But it's one of those little check boxes that should be done. And so one of the things that the real numbers have is the least upper bound property. So basically, if we have a sequence of numbers, that there's going to be a supremum. This is going to be the least upper bound. And so here we've got the blue dots, all the red dots are upper bounds, and then the supremum would be the least upper bound. So for instance, if we're looking at the rationals and trying to approximate the square root of 2, there's no rational that's the square root of 2. So we get a sequence of real numbers, rationals actually, that are getting closer and closer and closer to the square root of 2 from below. None of them are actually the square root of 2. So we add in a new number to the reals, the square root of 2, that now in some sense completes that sequence. So any sequence that is bounded is going to have a least upper bound. Okay, then we have the Bolzano-Viastro theorem, which we've talked about before. And so what this is basically saying is that one is that a sequence is sequentially compact if it only is closed and bounded. We've been doing it as if I give you a sequence of bounded numbers, it has a subsequence that converges. And the idea, so sequence of bounded numbers has a subsequence that converges. Without loss of generality, of course, my sequence is between 0 and 1, because where else could it be? So I divide in 1/2, and one of the two intervals has to have infinitely many numbers. So maybe there's infinitely many xn in here. And so we take the smallest index that's in this set. So let's call this one, we'll call it xn1. And then we divide the interval in half again. And one of the two intervals has to have infinitely many terms. Let's say it's the interval from 3/4 to 1, infinitely many terms. And so we take the smallest index that's in here, and we'll call that xn2. And we keep going and going and going like this. And so this gives us a sequence xn1, xn2, ... What can you tell me about the distance between two adjacent terms compared to the two terms before? Decreasing. By how much? Aha. So what you have is you have a sequence of numbers, and if you want, you can always look, they live between a left endpoint and a right endpoint. So you can have your AK, I'm not sure how it became green, but interesting, BK, and we'll have your X and K lives in here. And the ANKs are going up, the BNKs are going down, they converge to a common point, call that X. And so your sequence is going to converge to that. So we've done this before. I'm trying to do it a little bit quickly today. Okay, compact space. So we have lots of different sets, different notions of compact. Typically, we do a set as compact if it is closed and bounded. But there's another definition which is often very useful. It is the finite open cover property. If you have a set that is covered by open sets, then you only need finitely many of those open sets to cover it. So if I give you something that's non-compact, say the open interval 0, 1, I could let un be the interval from 1 over n to 1. So this is an open cover, no finite subcover. So it is very important that we have the endpoints for something like this. And so what we want to prove is that if you have the notion of compactness as closed and bounded, that is going to imply that if we have an open cover, we have a finite subcover. This is going to be very useful when we're trying to prove that a function that is continuous is uniformly continuous. All right, so we've already mentioned this one a little bit earlier when we talked about BolzanoViastro. If we have a sequence of nested intervals a and bn, and the an's are always going up and the bn's are always going down, because that's what it's nested, then their intersection is going to be non-empty. And in particular, if an and bn are always decreasing their separation by a factor of 2, they converge uniquely to a point. And so we've talked a little bit about why this is true. These are, again, theorems that you would file under the, of course, this is blatantly obvious. And when we get to the intermediate value theorem, that will be another entry in that beautiful, beautiful list. But you do need to prove these a little bit rigorously. All right, so the reason we really want this is we want to show that the interval 0, 1 is compact. So the proof, let's say here's 0, 1, and let's say we can write 0, 1 as a union, and it goes from 1 to infinity of, say, On, where our On's are open sets. And let's assume that there's no finite subcover. So here I'm using my notion of compactness is that there is a finite subcover whenever there is a cover. But what I do is I break my interval in half. And if there's no finite subcover, at least one of the halves cannot be covered with just finitely many of the O's. Which one would you like it to be this time? All right, let's do the right. All right, we'll do the left. All right, so without loss of generality, left not covered by finitely many. So now what do we do? Shampoo, right? Lather, rinse, repeat. Right? Here's 1/4. So we'll do shampoo. And actually, we should really write shampoo with the 2 O's next to each other to make it look like it's infinity, so that we keep doing this an infinite amount of times. So that's the correct way to spell shampoo when you're doing mathematics. So we keep doing this, and we're going to get a sequence of nested intervals. And the sequence of the nested intervals can never be covered by finitely many. So if you look at what's going on, we have a an and a bn, and it's going to converge to basically just a point, right? Well, because we have 0, 1 covered by open sets, that x has to be in some open set. So there exists, whoa, oh no. Any way to restore that? This may be the last time I use. Did everything vanish? All right, so this will probably be the last time I ever use the iPad for something like this, if it just vanishes that well. Oh well. All right, so let me just quickly put the stuff back in the slides. I guess I'll put the stuff back in the slides later. All right, so we had 0, 1. And so what we're going to do is we were doing all right, so the shampoo mathematics. And so what we're going to do now so it's now changed the thickness of everything. This is amazing. All right. So what we started with was we had 0, 1. We had the point 1/2. We had us interval 0, 1 could be written as a union. N goes from 1 to infinity of the open sets ON. And we kept looking. We said that it must be maybe infinite. Oh no, well, we'll do it this way. We'll do infinitely many. And then we would look at maybe 1/2 to 1/4. I'm sorry, 1/2 to 3/4. Infinitely many. And so we had our AN and our BN converging to some point X. And this could not be covered with finitely many. But because there exists an N such that X is an ON, then we know eventually that it can be covered by finitely many, by just ON. And that's the contradiction. All right. So the next results, and I will talk about the proofs of these later if we can, if we have time. Or just maybe give a quick sketch right now, is the intermediate value theorem and the mean value theorem. So the intermediate value theorem says that if I have a continuous function from A to B, and I look at the value the function takes on at A and the value it takes on at B, if I take any number between those values, then there is some input between A and B which takes this on. And one way to prove this is to essentially say, well, we can look at all the places where it's less than that and all the places where it's greater than that. Again, do these kind of sequences and convergence arguments. I'll leave that to you, or if there's time at the end, we will talk about the proof. The nice consequence of this is the mean value theorem. We are going to use this potentially. It basically says that if you have a continuous differentiable function on AB, then at some point in time, you're traveling the average speed. And if you think about it, well, let's say my average speed is 50 miles per hour. And let's assume I'm not traveling at 50 miles per hour at either of the endpoints, otherwise it's trivial. If my speed is always below 50 miles per hour, I can't have 50 as my average speed. If my speed is always greater than 50 miles per hour, I can't have that as my average speed. So at some point in time, my instantaneous speed is below 50, and at some point in time, it's above 50. Unless, of course, it's always 50, in which case this is really easy to prove, because every choice of C would work. And so if at some point in time I'm below my average speed and at some point in time I'm above my average speed, how do I know I have to be my average speed at some point in time? By the intermediate value theorem. And there's probably a reason why this slide is such that the intermediate value theorem is on top and the mean value theorem is right below it. It's a really nice application. Okay. So it's now somehow changed how it's presenting things. All right, so the next one is the extreme value theorem. And again, I'm going to just quickly talk about it now, and then if there's time, we'll circle back to this later at the end of the day. One of the great advantages of a compact set is that if you have a continuous function on a compact set, it attains its maxima and its minima. And so one of the standard proofs is you first show that if you have a continuous function on a compact set, it's bounded, and then you go from the boundedness to it attains its extreme value. And again, you can always play the standard games. Assume that you don't attain your maximum. Well, if it's not bounded, I can get a sequence of points where it gets arbitrarily large. But because it's a compact set, the sequence of points where it's getting arbitrarily large has a subsequence that converges. And then by continuity, I just get a small little neighborhood about that. And then that will get me a contradiction. I can't get arbitrarily large. And then once you have that its boundedness, then you basically just use like the least upper bound properties and get the extreme values can be attained. Okay. So now what we want to do is we want to talk about what does it mean for a function to be uniformly continuous. When I teach calculus, I don't really use this because this requires some concepts and analysis, but let's try to do it today. All right, so I want to see if I can No. Because I think this is just going to give me really thick. Yeah, it's giving me really thick today. All right, my daughter will fix this for me later. So a function is uniformly continuous if for every epsilon there exists a delta such that for every x and y in x, if the distance between x and y is less than delta, then the distance between f of x and f of y is less than epsilon. So the notation here is a little bit more general because I'm not assuming that my inputs and my outputs are both real numbers. My inputs are in one space, the outputs could be in another space. And I'm just saying that the distance between the outputs is always going to be less than epsilon if the distance between the inputs is always less than epsilon. So this is a truly wonderful result because it says that we don't have to choose a different delta for each value of x. So we know that there's a value that works for each x. And then the question is, how do we go from a value that works for each x to a value that works for all of them? And so what I'm going to do is I'm going to just sketch that continuous on a compact set, say 0, 1, implies uniformly continuous. So here is the interval 0, 1, and you give me any x, and then there's some neighborhood, let's say a ball about x of radius delta x. And I'll put a little epsilon to remind myself that I want the value of the function to differ by at most epsilon between any 2 points in this ball. So maybe a subscript is not the best way to do it. Maybe what I should do is just write it over here as a triple. Now I've got a ball centered at x, radius delta x, and any 2 points in this ball, the difference between the values of the function will be at most epsilon. Or if you want, you could say maybe the difference between f of y and f of x is at most epsilon, and just doing it about that point here. By using the triangle inequality, it really doesn't make that much of a difference. So it's a nice exercise. You can basically show all of these arguments are going to be correct up to epsilon or epsilon halves or 2 epsilon. You might have to put in some little factors like that as you use the triangle inequality. The idea is to give you a sense of how these arguments work. So what can we do? We can construct an open cover. So we get an open cover of 0, 1, and let's do it by balls about points x of radius delta x over 2, and maybe epsilon over 2. So that gives us a little bit of extra support. Is now that whenever we have the difference between the functions, it's going to be at most epsilon halves. So if I have to do like a triangle inequality and I double things, I'm still going to be okay. I'm making the radius a little bit smaller than I need, I should be okay. What must be true about the union of these balls? Your cover is 0, 1, so what must I be able to do? Finite subcover. So you get a finite subcover. Say it's going to be the union, k goes from 1 to n of ball about xk delta xk over 2 epsilon over 2. And now basically take delta to be related to like the minimum of the delta xk's. And I'll let you put in the rest of the details, but now if I'm very close, you basically want to say I'm within a ball. Well, I might not be within a ball of radius delta x over 2. And that's why I halved all the balls to give myself a little bit of flexibility in expanding things out. So it's a good exercise to go through and put in the rest of the details to show that a function that is uniform, that is continuous, is uniformly continuous. Okay. And then, right, okay, so actually I had given myself a blank slide over here to do that, so we can skip that. All right, so now we are ready to state the fundamental theorem of calculus. We will then prove it, and then we will go back in time, and as much time as we have until it's 11:50, we'll just talk about the analysis prereqs. So here, I went to Math World. The Wikipedia statement is pretty similar. The first fundamental theorem of calculus says that if f is continuous on a closed interval AB, and big F is the indefinite integral, also known as the antiderivative of f, then the integral from a to b of f of x dx is big F of b minus big F of a. This is missing something, or something is implied in this statement. What is implied? Well, so I almost wore my Ohio State shirt. I normally wear Ohio State when I teach this. Why? What's the full name of Ohio State? The Ohio State University, right? So we don't talk about the, well, actually they do. And that's a very bad word to use, is an indefinite integral. What word do I need to say for this to have some content? Not that. Well, I mean, the indefinite integrals will only differ by a constant. So when I subtract, it doesn't matter. If I don't say a certain word, this is essentially a definition. There's no theoretical content. So what does the integral from a to b of f of x dx mean? Well, if it means the antiderivative, then this is just a definition. Yes. It's the area under the curve, right? If you want to sing praises of the New York Yankees, that will almost make me as mad as this. It would be close. Okay? If you don't mention area, this is just a definition. It doesn't deserve fundamental. But as soon as I say area, and here is my function, f of x, and here is a, here's b, and now I'm looking at the area under the curve. So this is area. That's the content of the theorem, that the area under the curve is given by the antiderivative at b minus the antiderivative at a. If I don't say area, there's no content. Okay, so we want to prove this. So how do we prove it? So the first is we look at what's called Riemann sums. And so, given our function over here, what we're going to do is we're going to chop up the interval into pieces. 1 over n, 2 over n, k over n, k plus 1 over n, and 1 is just n over n. So without loss of generality, I'm assuming my interval is 0, 1. Is that a big deal? There's only one time when it matters. If my interval goes all the way off to infinity, then it matters. As long as my interval is finite, I can always translate and rescale to make it 0, 1. And so we really are developing the theory for a finite integral. And so what I do now is I chop up my function on these different intervals. And what I do is I approximate as follows. So I'm going to just zoom in on one section. Here is k over n. Here is k plus 1 over n. I'm going to deliberately draw like a wild function. And so here is my function. And what I can do is I can look and see at what point is my function largest. And I'll call this point uk. And I can see at what point is my function smallest. And I'll call that lk. And what I can do is I can get a rectangle here that will give me a lower bound. And I can get another rectangle that will give me an upper bound. Okay, so I'll pronounce it very carefully. F of uk times 1 over n will be for my upper bound. F of lk times 1 over n will be my lower bound. And then the true area of the kth piece is in between. Okay, so we all comfortable? All right. So we know we'll call the lowest sum on n is going to be the sum k goes from 1 to n of f of well, let's do like a 0 to n minus 1. F of LK 1 over n less than equal to the area less than equal to the sum. K goes from 0 to n minus 1 of f of UK 1 over n, which is the upper sum of n. No, because if you look at how I'm defining my intervals, I'm going from k over n to k plus 1 over n. So I have k intervals. The first interval goes from 0 to 1 over n, and the last is going to go from n minus 1 over n to n over n. One piece is not going to make a huge difference one way or the other. So the first thing I want to do is I want to show that the lower and the upper sums converge. So if I can show that the limit as n goes to infinity of u of n minus L of n equals 0, it converges to what? Yeah, there's nothing else it can converge to. You know, the area lives between them. So we know this is just the sum. K goes from 0 to n minus 1, 1 over n of f of UK minus f of LK. Now, how would you estimate this? So one thing is, we have a 1 over n, which is going to make things small. Unfortunately, what's going to make things large? So what do we have that makes the sum large? Or, I'm sorry? Yes. Yeah, the number of summons. We have n summons. So because we have n summons, that could cancel the 1 over n. So the only way we're going to win is if we can show f of UK minus f of LK is uniformly small. So we win if uniformly small. Okay, how would we show that this is uniformly small? There are two approaches based on slides you've seen earlier today. Can somebody tell me one way to try to show that this is small? So you might have to assume more things about little f, but as long as you state them publicly, otherwise become a philosopher or an economist. Okay, good. Well, we actually have already assumed that f is continuous. So we can use uniform continuity. So one approach is uniform continuity. There's another approach using a theorem I stated earlier today. Yes. Not the extreme. The mean value theorem. How many people ever watched the TV show Friends? Have watched the TV show Friends. Except for 2 episodes, what does every episode's title begin with? Nope. The one with. Everything but I think 2 episodes is the one with. And so when I normally give this lecture, because I don't have the benefit of using uniform continuity, I call this the lecture, the one with the mean value theorem. And when in doubt, if you need to guess something, guess the mean value theorem. The mean value theorem is the poor mathematician's Taylor series, right? You know, let's look and see what's going on. So if we use the mean value theorem, you know, f of UK minus f of LK is equal to f prime of CK for some CK times UK minus LK. You know, there's some CK in the interval. So UK, LK, CK are all in the interval K over N, K plus 1 over N. So what can you tell me about the size of UK minus LK? How large can that be? One over N. So the absolute value of f of uk minus f of lk is less than or equal to 1 over n times f prime of ck. If f prime is bounded, then we get the sum k goes from 0 to n minus 1 of f of uk minus f of lk, and then we had a 1 over n, is going to be less than or equal to 1 over n, the sum k goes from 0 to n of b times 1 over n. Oh, sorry, up to n minus 1. And we get an extra factor of 1 over n. And because of that extra factor of 1 over n, the sum hits that, and we're left with b over n. And so now this is one of the reasons why I wanted to do this lecture today. In the last class, I talked about how frequently in analysis, we don't really care what the bound is, so long as there's some bound and it's finite. Do I care what the optimal b is? Oh, maybe if I was actually computing this and I wanted to know what is my error, sure. But if I'm just trying to prove that in the limit, it's given by the antiderivative, it doesn't matter what value b is. As long as it's something that's finite, it's going to go away in the end. Yes? Yes. Yes, absolutely. Agree completely. And that's the disadvantage of the second approach. We need f prime to be bounded. And of course, when I say f prime is bounded, implicit in that is that f prime even exists. So this is a bit more restrictive. That said, think back to the functions that you integrated back in Calc 1 and Calc 2 and Calc 3. If you'd like to share with me after class how many times you had a function that wasn't differentiable that you integrated. I have to run off today immediately after this class, but I'm really not worried about too many people coming up with things to share with me, right? All the functions you looked at were differentiable, and they were all bounded on intervals. So in terms of the functions that we actually use in a day-to-day sense, it's actually not that bad of an assumption. When I was a college student, I was always furious whenever they had these extraneous assumptions on theorems. I wanted theorems proved in as great generality as possible. And then I started doing real math and not just homework problems. Like, well, of course my function's infinitely differentiable. Why would my function not be infinitely differentiable? And you start to realize that in practice, the problems that you're interested in using, frequently you have really nice properties on the functions. It is, of course, useful to know what is the greatest, most general case that you can apply this to. So this is a little bit weak because it needs the mean value theorem. So let's go and now do approach 1. So no f prime assumption. So we have the sum k goes from 0 to n minus 1 of 1 over n of f of uk minus f of lk. What can we say about this sum? What can we say about f of uk minus f of lk? I'm sorry? Right, so for all epsilon greater than 0, there exists a delta such that if x minus y is less than delta, then f of x minus f of y is less than epsilon. Choose n so large that 1 over n is less than delta. And so now we're using uniform continuity. And so now this implies that we are now less than or equal to the sum k goes from 0 to n minus 1 of 1 over n times epsilon. And what does that sum equal? Epsilon. And now you say, since epsilon was arbitrary, the limit is 0. Or if you want, you could say, since epsilon is arbitrary, and do things in the present tense and not talk about it. That's essentially the only real choice you have as to how you phrase it. Because we showed that the limit of the upper sum minus the lower sum as n goes to infinity is less than epsilon for any choice of epsilon, then in the limit, the only possible value is 0, because I could always just choose a smaller epsilon. So we actually are able to prove that the upper and the lower sum converge. Wonderful. and they converge to the true area. Yes. Yes, and I actually even said that. I did say for all epsilon greater than 0. We showed that the limit is less than epsilon for any epsilon. Or if you want less than or equal to epsilon for any epsilon. So you choose epsilon to be 1 over a billion, and I know that the limit is no more than 1 over a billion. You choose 1 over a quadrillion, it's no more than that. Okay, so we now know that the upper and the lower sums converge. They converge to a common value, and it is the area under the curve. Now we just need to compute what they are. And so how do we do this? So now we want to compute UN or LN. All right. But what we're going to do is we're going to do a telescoping sum. So let's look at F. Let's look at the sum. K goes from 0 to n minus 1 of F of x k plus 1 minus F of x k. What does this sum equal? So it's F of x1 minus F of x0 plus F of x2 minus F of x1 plus F of x3 minus F of x2, yada, 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 plus F of xn minus F of xn minus 1. What does the sum equal? Yeah. We just see everything is canceling, right? And it's just going to be F of xn minus F of x0, which is just F of 1 minus F of 0. So what's interesting is it doesn't really matter how I partition things. I'm going to get the same value. Okay, why is this useful? So we know that the sum k goes from 0 to n minus 1 of F of xk minus F of, I think, what do you want to do? F of xk plus 1 minus F of xk is equal to F1 minus F0. How can we view F of xk plus 1 minus F of xk? What could we use? Yes. The mean value thing. I was debating, should I play the music from Friends, right? This is the episode, the one with the mean value theorem. And I really want to drive home when you're looking at the difference between two functions, if they're really close, the mean value theorem is terrific. This tells us that this is equal to F prime at some intermediate point. So we need to give it a name. I've already used the letters X, C, U, L. We could do X star. I was thinking W for Williams. Or if there's anybody we want to donate money, maybe we can name it after them and hopefully no. All right. So it'll be F prime at WK times XK plus 1 minus XK. Well, what is big F prime? It's just little f. So it's little f of WK. And what is XK plus 1 minus XK? Yeah, because this is K over N, and this is K plus 1 over N. So now we have this beautiful result that the lowest sum is less than or equal to, and we have the upper sum over here, F1 minus F0, which is the sum, K goes from 0 to N minus 1, of 1 over N F of WK. Right? But as N goes to infinity, what does UN and LN converge to? It converges to the area. And this sum in between, well, it makes sense. If I choose some points WK that live in here, wherever the point WK is, it gives me some approximation to the area. It's going to be at least as large as what happens when I use LK. And it will be no larger than what happens when I use UK. So it's going to be somewhere in between. And if my function is nice, as the interval gets smaller and smaller and smaller, it should become a better and better approximation. What's wonderful is even though those points are chosen in a terrible way, where we don't immediately know where they are, we know that their sum is always f of 1 minus f of 0, independent of where these points wk are. It somehow all works out together. So what does that tell us that f of 1 minus f of 0 has to be? It has to be the area. And so we are left with f of 1 minus f of 0 equals the area under y equals f of x from x equals 0 to x equals 1. And this is the proof of the fundamental theorem of calculus. So if we're willing to avoid some results from analysis, if we're willing to assume that our function is differentiable and has bounded derivative, we don't need all the advanced analysis machinery. If we want to have the weaker possible setting, then we now start to use the concept of uniform continuity. So out of curiosity, how many people had seen a proof of the fundamental theorem of calculus at some point in their Williams career? How many had seen a proof before coming to Williams? Okay, so not that many. This is something that should be proven. You don't get to fundamental lightly. Right? There's one other fundamental theorem that you may have seen, depending on what classes you've taken, except they don't call it fundamental, they call it central. The central limit theorem from probability. That's really the fundamental theorem in that subject. We will actually get to that in this class. We will actually get to the fundamental theorem of arithmetic as well, so that by the end of this class, you'll have at least seen proofs of 4 fundamental theorems, some of them multiple times. All right, so we've still got, on the order of 7 minutes left. Now you could ask other questions about, well, if I have different partitions, do the UNs go monotonically down? If you choose your partitions to be a refinement, where you go from 1 point to 2 points to 4 points to 8 points to 16 points, then you will have something like that. But if you don't, then you could have some strange things happening, and it will converge, but yes. Yes. So what you would want to do is you would want to show that as you go off to infinity, that you have some kind of convergence.
Well, that's the per function basis, like you can't do that.
Right. So what you can do is you can prove it on an interval of any finite length that this is going to be the case. And then you take the limit as that length goes to infinity. And you can play that game. But so this was the fundamental theorem of calculus, less than 50 minutes. What part of analysis do you want me to review from the beginning? So we had some results from analysis. We had the intermediate value theorem. We had the mean value theorem. We sketched the proof of compactness implies finite subcover. It's not bad to just go through and just try to put in the details yourself. Maybe it's not a bad thing that the slides deleted. I actually thought it was strange because it was giving me a different toolbar on the bottom, which I actually liked better. But somehow I guess it also has an erase everything button without a, are you sure you want to do this? So anything from the analysis that you want to review? I'll just make a few comments on the mean value theorem. So we have, say, f of x minus f of x naught over x minus x naught is f prime of some point c. Right. We can rewrite this as f of x is f of x naught plus f prime of c x minus x naught. This is exact. The tangent line, so if I have my function over here, and here's my point x naught, and so here's my point x naught, f of x naught and the slope is f prime of x naught is my slope, then the tangent line is y is equal to f of x naught plus f prime of x naught, x minus x naught. So if you look at the mean value theorem, this basically gives you a way to talk about how close is the tangent line to your function. And so you could study, f of x minus y, that's going to be f prime of c minus f prime of x naught times x minus x naught. And so we can use this to try to get a sense of how accurate is everything. What might you want to assume about f prime? I'm sorry? It would be nice if it's smooth. Good. So, but smooth is really, really severe. Smooth is saying infinitely differentiable. So what's a little baby step towards smooth? Yeah, one's differentiable, right? So what would you then use to study this? The mean value theorem, right? When in doubt, use the mean value theorem. If we assume f prime is differentiable, then f prime of c minus f prime of x naught, we can just use the mean value theorem. And then what we would get is we would get f of x minus y is going to be less than equal to, oh, I'm sorry, we have an equality, is going to equal f double prime at some point, say c tilde, and then we'll have, we had, I think, c minus x naught. So we'll have then c minus x naught over here, and then we had, I think, x minus x naught. And we'll put everything in absolute values. Now, what can you tell me about c minus x naught? Well, that's clearly less than equal to x minus x naught, as c is between x naught and x. So the error is f of x minus y. That's going to be less than or equal to f double prime of c tilde times x minus x naught squared. So if this is bounded by, say, b2, then you get the error is less than equal to some constant b2, x minus x naught squared. So when you're doing the tangent line approximation, the tangent line, you're moving on the order of x minus x naught, but your error is on the order of x minus x naught squared. So if x minus x naught is of size 1 over 100, then the error is roughly of size 1 over 1,000. If the error is of if x minus x naught is of size 1 over 1,000, then x minus x naught squared is of size 1 over 1,000,000. And this gives you a sense of just how much better things are. But if you look at what we're doing, this really looks like the beginning of a Taylor series. The Taylor series is just f of x naught plus f prime of x naught, x minus x naught. The mean value theorem chooses some point c to make it an equality. And we can use this to then just see how much of an error are we making. All right, so this basically finishes up what I wanted to do today. It is a nice application of some of the results from analysis. It shows you how we can put them together and how we can remove the assumption that our function is differentiable and bounded derivative. And it gives you some idea of why we care so much about these theorems from analysis. All right, have a good day all.